Hello and welcome to this video titled A History and Purpose of the Internet Protocol. In this video, the topics I'm going to cover are the early development of packet switching and what is packet switching. We're going to define that and see why it was something that needed to come about. And we're going to do an overview of the Internet Protocol. So let's get started. So let's start with packet switching. After all, IP was developed in the response to the need for packet switched networks. Why were packet switched networks developed? What need were they developed for? Well, way back in the early days, maybe even before some of you guys watching were even born, back in the late 1950s to early 1960s, early networks relied on dedicated telephone lines between disparate networks to transport data. What does that mean? Well, from the earliest days when Alexander Graham Bell invented the whole telephone network and people started stringing up telephone wires all throughout the country and throughout the world, initially those telephone wires were used to transmit electrical energy, but that electrical energy carried your voice. So you would pick up the handset, whatever it looked like back in the late 1800s, you would speak into it. As you spoke, the air coming out of your voice would vibrate like a magnet in there, which would create an electrical current that would vibrate sort of in parallel to what your air was doing coming out of your vocal cords. So that electrical current vibrating at different frequencies and rates would go along these telephone lines, and at the other end, the electrical current would then vibrate another magnet in the receiver, which would push out air, which would be your voice. Well, not long after that, people realized, hey, we could also use this exact same technology, these exact same wires, to transmit data as well. And so they started using it for that. So now in the early networks, it looks something like this. You might have a company right here and a company right here at the other end of these telephone lines, and maybe another company right here with some telephone lines between them. If I can just imagine those are telephone lines right there. So let's just say this is, and these weren't really private companies, this was all developed for like government agencies and universities and colleges and things of that nature. So here we have, let's just say University A, University B, and University C. Well, back in the early days, in order to transmit data, you would actually have separate computer systems. So there would be a computer system that linked University A, I'll just put here CS. That would be their big mainframe computer that would connect to these wires right here, and that would connect to the computer system in Company B, which connected to those wires. Now, if University or College A wanted to send data to the computer in College C, they had to move over physically. They had to actually move into another room where there was another computer system, sit down in front of that terminal and start typing data, which would go over different telephone lines to reach location C. So some people started saying, wait a second, this is ridiculous. I have to keep getting up and moving around between different terminals in my room, or different terminals in different rooms of my building, or maybe even different buildings in my entire company here. Wouldn't it be nice if I could just sit down at one terminal and maybe address my data in such a way so that when the data left my terminal, it knew which system to go out on? And so instead of using these dedicated wires that go over here, these dedicated wires over here, wouldn't it be nice if somebody could invent some system that had in each location, A, B, and C, a dedicated device, we'll call this a networking device, and when my terminal connects to that networking device and I start sending data, my data will actually have some sort of address in it, and this terminal device will know, this computing device, this networking device will know, oh, based on where this data is going, I need to choose this set of telephone lines to get it out, or this set of telephone lines to get it out. So that is what precipitated the need for packet switched networks. So as we can see here, in the early 1960s, this concept of packet switching was developed by an American computer scientist called Paul Barron. And what he called it back then was not packet switching, but something called distributed adaptive message block switching. You'll never need to know that. You'll never be quizzed or tested on that in any exam, but this is just sort of showing how IP came to be in the first place. Okay, so this guy sort of came up with the concept of how could we do this? How could we structure data? And he thought, well, hey, rather than just sending a long stream of data down these telephone lines right here, data's done, move over to the next terminal, send a long stream of data down those wires to that location. He said, what if we did this? What if we cut our data up into little blocks, what we now call packets? But he didn't call them packets back then. He said, let's divide the data up into little blocks, and let's have each block have an address of maybe where it came from and where it's going. And that way, if somebody else sometime down the line, because he didn't create the networking system, he didn't create routers, but if somebody else down the line comes up with a networking device that can recognize these addresses and send data this way or that way based on its address, now we have a packet switching method. So the basic concepts of packet switching, as defined by the gentleman we just saw in the last slide, were these. Packet switching needed three components. We need to use a decentralized network with multiple paths between any 2 points. We need to take data and divide it up into discrete blocks, what we now call packets. And the delivery of these messages needed to be done by store and forward switching. Now, in case you're not familiar with that term, store and forward switching, when switches first came out, way back in the dark ages, the idea was this. If you're a switch, if you're like a really early switch, and I'm sending you a stream of data, well, the address of where that data is going is at the very beginning of the data. You don't have to parse too far into the bits to find where that address is of where it's going to. So the idea was, if you're receiving a stream of data and it's coming in on your port number 1, let's say, you only have to buffer in a little bit of that data to be able to read the address, just some of the data at the front end. Once you know where the address is and you, the switch, determine that, oh, this data is actually going to go out port number 8, now you can start forwarding it out port number 8, even though I'm not actually done sending it to you yet on port number 1. So imagine that now. The data is coming in on port number 1, the electrical signals, the bits are still coming in, and at exactly the same time, you're switching it out on port number 8 because you already saw the address field at the very beginning of that data. Now that was called cut-through switching. Now, not a lot of switches do that these days because several decades ago, people realized, well, wait a second. What if there was something in that data that was bad? Like, what if that frame was corrupted in some way? It's too late. It's already gone. It's already going out the egress port. So some people said, hey, maybe it'd be a better idea for the switch to just buffer and take in all of the data from beginning to end, even though it knows the destination pretty quickly, just store it all in memory, and then once the data is stored in its entirety by the switch, then switch it out the egress port. That way the switch can decide, oh, this frame is corrupted, it's bad in some way, we can discard it. Or you can do other things as well. And that was called store and forward switching, which is what most switches do these days, store and forward switching. And you can see here, this was a critical component of packet switched networks. Now, a few years later, in 1973, the U.S. Defense Advanced Research Projects Agency, okay, after they were done studying aliens in different galaxies, they shifted their focus and they said, hey, we need to, there's now packet networks out there, okay, so it had been, 6-7 years since Dr. Barron had come up with his packet switching concepts, and some packet networks had started being developed, but they were different, they weren't homogeneous, they were definitely not connected because they operated in different ways. And the U.S. Defense Advanced Research Projects Agency, there's a mouthful for you, they said, hey, we should come up with a way of linking networks, maybe not every network, how about just the networks that we, the military, use? Because after all, if we have a radar system that's detecting an incoming missile and somebody blows away that radar system, how are we going to let other networks around us know that, hey, get ready, a missile's coming in? So they said, hey, we should connect all these radar systems, and this was actually the basis of all this. They wanted to interconnect radar defense systems together in a network that was resilient, so that if one part of the network got taken out, messages and warnings and stuff could still get to end systems through redundant paths by using packet networking or packet switching. So in 1973 is when it really took off, because the US government got behind this and started really building out these packet networks, and they put a quote out there. They said, hey everybody, all these different companies, we need some standardized way to do this. Because right now, nobody's really agreed on what the addresses should look like. Should there be a source and destinations or anything else that needs to be appended to the data when it goes onto a network? So we need some standard created. So they put out a request for different companies saying, hey, why don't you guys all put your quotes together as to how you would do it, and whichever one we select, we'll give you, a crazy amount of money and we'll start developing it. Well, this is how TCP/IP was invented. This came from one of the companies that came up and they said, hey, here's our response to what you want. And TCP/IP was developed, and here it is, the de facto standard today. So TCP/IP actually originally was one big program. There was no separate TCP and IP. It was all together. And then later on, they decided to break it out and make TCP functionality different than IP functionality. So right now, just real quickly, we're going to focus on what is the Internet Protocol. What is this thing that came out in response to DARPA's request to get this going? So IP has been around, as you can see, for decades. It's been around for a long time. It's currently, well, the current version of IP is actually IP version 6, but IP version 4 is still predominant. So right now in the world is IP version 4 and IP version 6. IP version 6 is starting to gain more and more traction. This video series is not about IP version 6, but here at INE we've got lots of other videos that do go into that. Here we're focused mostly on IP version 4 in this course. And that has been pretty much the standard for the last several decades. Even today in 2019, you're going to find vastly more devices running IP version 4 than IP version 6. So let's talk about IP version 4. Now you might be saying, but Keith, what happened to IP versions 1, 2, and 3? Well, you can Google that. There's some interesting historical reading for that, but I'll tell you what, you will never in your lifetime find any devices running IP versions 1, 2, or 3. Okay, they just don't exist. Everything runs IP version 4. So IP version 4 resides at the OSI layer 3, the network layer. So if you're familiar with the 7 layers of the OSI model, the Internet Protocol takes up layer 3, the networking layer. It is connectionless. What does that mean? That means that some protocols, when they take the data and the protocol says, hey, I'll take your data and I'll send it to its destination, some of those protocols first will say, hey, but before I do that, let me make sure the destination is actually there. Let me make sure he's alive. Let me make sure that he's ready to process my incoming data. When I send my data to him, let me get an acknowledgement back to make sure it actually got there. That's considered a connection-oriented protocol. IP does not do that. So in the development of IP, so remember, TCP and IP were originally together, and TCP actually does do that thing, but then they decide to split TCP off from IP and have them as both standalone protocols. So IP by itself has no reliability, no verifications that the destination exists. All IP says is, hey data, give me your data, or application, give me your data, and I'll put a header on the front of it that has a bunch of information like where this data is coming from, where it's going to, maybe a few other things, and then I'll just send it out on the network. And IP says, I'm not going to make any guarantees that the destination exists, that it got there. If you want that type of information, you'll have to get it elsewhere from like TCP or something else. So IP itself is connectionless. And what IP really does is it provides, like it says here, an encapsulation method. It gives you a header and an addressing structure for data to be transmitted across routed networks. So that is the sort of history and intent behind the Internet Protocol, was to be able to take these discrete chunks of data, give them a header or a wrapper, and that wrapper would be sufficient to put it into the network, and the network could look at that header and know how to get that data to an ultimate destination. And as we go through here, we'll dig into what that header looks like, what those addresses look like, but that concludes this video on a history and Introduction to IPv4.